All right, guys, welcome back. Hopefully everybody had a good reading week. So your test number 1 will be next Monday. So I haven't got a PDF guide yet, but I do have something on my iPad. Also, it's on the template PDF as well. I will make sure it's in the proper format a little bit later today, but I can also go over with you the coverage and the format of the test. I'll do that right away. Okay, and then we'll continue with the graph. All right, let's now take a look. Sorry, just some announcement very quickly. So your assignment number 1 is going to be due this Wednesday. So try your best, especially for the programming part. I think that part there is not challenging algorithmic-wise, but I think it's really important for you to understand about the interpretation strategy for each list. That's really going to give you the insight. And after your test number 1, I'm going to talk about another 2 implementation strategies for graph. Those are the more common ones because they're somehow more efficient in certain scenarios. But we'll do some comparison table at the end. But you definitely want to finish your assignment number 1. And also about the depth first search practice as well. Make sure you do that, and we can also go over the solution as well when we meet together on Friday. Okay, your test number 1 next Monday. Okay, guide is not yet released. I will do that either today or tomorrow. Not yet, okay? But I definitely can confirm with you the coverage and the format. I'll do that in a moment. Okay, so not yet. Maybe Tuesday morning, the latest. I just need to put it in the PDF form. But there will be 2 review sessions on Wednesday. I would suggest, since your assignment is only due on Wednesday midnight, about 11:55 p.m., I would say maybe on the Wednesday class, we make it more like a review session for. We can revisit any of the topics that we covered so far in the slides or even in the tutorial that you have any doubts, we can go over them. Okay, so that's going to be really your time. We can spend up to 80 minutes on Wednesday, just go over everything you want me to go over, except for the assignment, because that one's actually due, not yet due on that particular time. And then on Friday, we can do another review. And that one there, we're going to focus more on A1 specifically. Especially, I want to maybe not necessarily going from scratch because that'll take a long time. We only got 18 minutes on Friday. I can potentially go over some selective methods in the edge list graph. And just to show to you what you should really watch out for, especially some runtime that you want to watch out for. Okay, so that'll be the plan. Okay, Wednesday and Friday, we're going to hopefully focus on getting you prepared for your test number 1, Monday next week. Okay. And then you definitely, at the same time, review your tutorial exercises as well. I think for tutorial week number 4, so that's the one we assigned to you, some exercise on tree rotations. I also posted the solution yesterday. So you can also take a look at the Java code. If you have any doubts, we can also go over part of it, maybe on Wednesday as well. Okay, so all the resources are there. Okay, so please make sure you start review. You got exactly 1 week to get prepared for the test. Okay, let's talk about the test itself. So the PDF I'm going to release is going to be more or less this. So this is already on the lecture site. You can also feel free to download it right now. But let's go over. I still need to confirm the room, but it's going to be Williamsville Center, not in the lecture room. So it's going to be Monday. Oh, forgot to put the dates. It's going to be next Monday. So it's going to be Monday, October 27. Okay, it's not going to change. And then I can only for now secure 15 minutes, but don't worry, I'm going to adjust the question accordingly, so you'll be sufficient, will be appropriate for 15 minutes. So please make sure you come at 4:30 to the Williamsville Center, and then it's going to take 15 minutes. So I'm going to reboot the machines into lab test mode for 15 minutes. And then what about the coverage? So all the lecture materials that I'm going to cover until including today. So today, I think I want to revisit about the depth first search a bit, just to see how we can understand certain properties of depth first search. And also, if time permits, I want to also go over a bit about breadth first search as well, at least how it works intuitively. There will be certain deeper properties which we can compare with depth first search. We can do that maybe after the test. So that one wouldn't have to go to the coverage for your test. So whatever we cover until today, including today, will be covered in the test. But I'll definitely confirm about which slide you should really study to. And all the tutorials, and also your assignment number 1. Okay? Of course, you only got 50 minutes. I cannot really put everything in the test. It's not possible. So I need to be selective, but I just cannot tell you exactly which topics I'm going to put in the actual test. Anything's possible. So I would suggest, please just make sure you study carefully with all the covered materials. Okay. And what about the format? Okay. So there will be two parts, as I kind of hinted on day one of the term. So the part number one is going to be more about programming. Okay. So this part here is going to be basically driven by JUnit test cases. So the format will be identical to your assignment number one. You will be given JUnit test cases, in which case you have to create the Java classes and methods accordingly. Okay, that's pretty much what you had to do for assignment number one. So you have to know how to import Java starter projects and also create different classes and methods. That's the part I can also review very, very briefly on Friday. We can do that too. Okay, so that's the part you definitely don't want to get any penalty on the marks. And then you're gonna implement the Java classes and methods to pass the test cases, right? But I can tell you that very likely the programming part will definitely include how you can implement some methods on the edge list implementation strategy for graph. Very likely. Okay, so you definitely want to review it. But before Wednesday, just make sure you complete the assignments. Okay, and the written parts. So the written part is going to be done over eClass. So that would mean please make sure you bring your mobile phone and make sure the dual mobile will actually work. Okay, so I will put that in the guide as well. You definitely want to log into some EECS lab machine. Doesn't need to be within Small Center. They're all the same. You can go to the LaSalle building, ground floor. Just make sure your dual mobile will actually work. So your dual mobile. Okay, verification. Primarily, it's going to be multiple choices. Okay, and then could be something about maybe definition, something about the properties of the graph, and etc. Right? Also asymptotic analysis, which we also review, and also binary search tree, tree rotation, self-balancing tree. You know, all the things that we cover. Right? It's very possible. Primarily multiple choices. There might be certain parts that will be require some type answer. So you may have to type something from the keyboard, enter some text box, and submit the answer. But it's also going to be done through eClass as well. So it could be some, excuse me, allergy. So we got something about short answers and also justification, or maybe some minor proofs. I wouldn't put too much proof, but it could be, you know, some maybe part of it. I'm going to save the more tedious, lengthy proof maybe for the exam, but we can talk about it once we get a little bit closer. Okay. Questions? Go ahead.
So we put the format like this. Are we going to get it's from 4:30 to 5:20, right? So are we only going to have like 30 minutes for the programming part, and then we have to move to the written part, or are we just going to have?
Of course, you know exactly how you balance between the two parts is completely up to you. So I wouldn't mind if you start with a multiple choice first, and then go to the programming, or the other way. As I said, what I will try to make sure is it's kind of fair and also appropriate for the 15 minutes. I wouldn't give you the whole entire assignment one to re-implement in 15 minutes, right? So I'll give you something to implement. Yeah. So whether you want to start with the eClass or you want to start with the Eclipse is completely up to you. But I can tell you, if I were you, I might do the programming part first, because in the worst case, if I really cannot finish the eClass part completely, I can still guess, right, in the options. So that would be how I think of it. But hopefully you don't have to run into that situation. Question?
Are the weightings for the program weighting the written like the same? Or?
How about this? I'm thinking about this. So for the weighting here, I want to keep this for now a little bit flexible in the sense that, let's say I tell you exactly what I'm thinking. I think that could be to your guys' advantage in the following sense. So, let's say for the eClass one, let's say the total mark is 100, let's say, for example. And also, let's say for also the programming part, there might be certain test cases you have to maybe pass, right? Something like that. Okay? Exactly how to weight it, I will rather maybe after we have graded everybody's submission, maybe I can try to adjust the ones you didn't do so well, a little bit lighter. You see what I mean, right? I want to leave a little flexibility over here. Rather than saying it's going to be 50%, 50%, right? I want to see how everybody performs. I'll try to maybe adjust the way so that it's going to be a little bit better for most people. May not be for everybody, but at least for most people. But you can think about, roughly speaking, it's going to be roughly half and half, roughly. Okay. Question?
Will future tests follow the same format? Or
Yep, you only got one more test, right? So it's going to be similar format, yes.
Okay,
Yeah. Yeah, exactly. Second, very good, good. So it's going to be programming part and also written part. Okay, good. The first one, I don't really want to make it too tricky, the first one. So as long as you do the study, make sure you do assignment 1, you should be good. Okay? Go ahead, question.
So, I'm just a bit concerned about the coverage.
Yeah.
Since there's like 2 parts.
Yeah.
And it's only 15 minutes.
I know exactly what you mean. It's somehow I really wanted to really reserve for 80 minutes, but somehow it's really difficult because for our scheduled tutorial, it's not in a lab. So I need to find some time gap in the either Williams Small Center or some building. It turns out that 1 hour is all we have. But as I said, I'll try my best to really make sure it's possible to do some programming and also some E-class. Okay.
So I had a question mainly about the programming one.
Yeah, go ahead.
Because I remember like in the previous course, we had like an hour to do your programming part.
Right.
And it still seemed quite long, at least just for
Yeah,
me.
I see what you mean.
How many questions will there be in the program?
I haven't really finalized yet. It could be that maybe only, don't quote my word for that, right? Just could be the programming part, you just have to implement about 1 or 2 methods for edgeless graph. That's it. That one there hopefully will take you about 15 to 20 minutes, for example. And then after that, you can still have about 20 minutes or so for your E-class. That's something I'll try to balance, for the actual one. Yeah.
Okay.
Yeah, for now, don't worry too much about it. It's, I'll try to design the test in a way I think that's doable for 50 minutes. Okay. Yeah, go ahead.
So since it's split, so then the programming part, we would submit it in the EECS web summit. Is that how?
Good question. So they will be, of course, I'll also make sure I put it on the E-class, the guide as well. But logically, the programming part, you will have to import the starter project into the Eclipse. Once you have complete whatever you have done, you can then export it as a zip file, and then there will be a link supplied to you. Click on the link, and then you'll do web submit just for that part. And then for the E-class, just click on different options, and then you'll be submitted automatically as well.
And the written part of the E-class quiz is going to be open through 4:30 to 5:20.
Yeah, so don't worry. So there will be very clear instructions. You can imagine that there will be some like a PDF as soon as you log in, and then the PDF is going to tell you, okay, here's the link for the E-class, and here's the link for maybe downloading the startup projects.
Okay.
Yeah, good. All right. All right, any other questions? Okay, good, thank you. Good, sounds good. All right. And then, so for today, I just want to talk a little bit more about that first search, and also we can do some breadth-first search as well. Okay, let's see. All right, let's do some very brief recap. Okay, so basically before the reading week, we spoke about the depth-first search, just about how you can mark the vertices and edges. Of course, when you actually study for the test, you're just going to remember what does it really mean for vertex to be either visited or unvisited. And for the edge, it's going to be either unmarked, it can be discovery edge, or it can be a back edge, right? So these are the 3. And for today, we're going to introduce another way of traversing the graph. It's going to be called breadth-first search. In that way, everything stays pretty much the same, except we still got discovery edge, yes, but rather than calling that back edge, we got something called cross edge. So that's something we'll see today as well. And we'll do some example too. Okay? So depth-first search, and later on breadth-first search. And that's a property. Yeah, I think Josh actually mentioned something about some counterexample. I still got to get back to that. I'll make sure I address that on Wednesday. Okay, I make sure I address that properly. But it's a property, right? So we did some proof before the reading week. So I think inductive proof, I do not think you will be expected to do the whole proof for test number 1. But you do want to get prepared for some inductive proof, I'm pretty sure, for the final exam. It's actually for about a month away, more than a month away. But I think for this test, just make sure maybe at least you know how to state the inductive hypothesis, and you can maybe show some very simple test case, some simple base cases, and that might be it. All right. So just make sure at least the example that we did in the class, make sure you go over them and make sure you're able to do things like that. I think for your assignment 1 question, you got 2 questions to do with the inductive proof. The first one there is very similar to the degree sum that we did in the class. That one just more like a practicing the format for inductive proof. The second one is slightly more complicated, but try it, and then we can go over the solution of that. I'm going to release the solution to you on Thursday, but we can talk about some of them on Friday. Okay, so there's a proof. And then, yeah, that's one of the inductive mathematical induction we did. All right, good. And then depth first search. Basically, the way to trace it is by using a stack right here. All right, last in, first out stack. And that's something we did. So I think the example you did in the assignment, that one's a rather complicated one. I think that's a good practice. Okay, so I would say what I can do, either I can record a video solution to it to really walk you through exactly what will be the order of the vertices being pushed or pop onto the stack or from the stack, and also about the different edges. Either I'll do that, or maybe you can just go over the solution together on Friday. We'll see either way. Okay, but definitely give a try on that example on the assignment. Any questions in general about how you can do traversal, doing depth first search, marking the discovery edges, back edges using the stack? I think the most important thing for you to watch out for is about the assumptions we are making. So in this case, we are saying that, let's say for A, the adjacent vertices, we got B, D, and E. What should be the order in visiting them? So here we say that we're going to follow the alphabetic order. So it's going to be followed, we're going to do B first. And then from B, we're going to extend as far as possible. So that's a principle for depth first search. But when we do the breadth first search in the second half today, it's going to be a little bit different. Okay? So the order is actually important. It's going to be impact the order that you push things onto the stack. So just watch out. Okay? Okay, so this is another example. So please make sure you do them, and I'll also post a solution as well. I'll do that in a couple of days. Okay, so you can compare. All right, so that's good. And then that's a more complicated one, but that's your assignment, right? Okay, so that's about application and adapting. So let's now go over this one here. Okay, let me just go to, I'll start with this for today. But before that, so this part here, definitely directly relevant to your assignment number 1. So that's about the edge list, okay? So one thing you want to pay attention to, in the programming part for your assignment number 1, I think somewhere in the test comments, I said there should be a requirement about big O of 1 performance, running time. Think about why or how we can actually achieve that. The hints would be, take a look at the doubly linked list. Okay, I will definitely tell you the answer afterwards, but you may want to think about it. All right. Okay, the doubly links, this is doubly linked list. You kind of learn from 2101. If you got any trouble understanding that, you may want to drop by office hour. Maybe we can catch up some basics. But that's something we cover. Make sure, especially for the remove. Okay. And then we got the edge list strategy. Okay. And I think this one is very visual, but very informal. I think the most important thing is for you to really see how the code works and maybe get into the programming. I think that's something you want to do. And your actual test is not going to ask you to implement so many things. Maybe 1 or 2 methods maximum. Okay, the basic one. Okay. Any questions about edge list in general? All right. I think assignment number 1 really kind of pushes you to understand completely about this strategy here. And then since we're going to cover another 2, the adjacency list and also adjacency matrix. I think for your last assignment, well, assignment number 2, we should do at least one of them. Okay, we'll see which one. Okay, just to make sure you're familiar with the graph structure. So the goal will be after this course, whenever you design your own algorithm on the graph, you can always know what kind of data structure you can choose. You can choose adjacency matrix, or you can choose the adjacency list to implement your graph. You need to get something working, not just on the paper. Okay, good. Okay, let's now go over some, first of all, let's go over some properties. Okay, and then we talk about some questions. Okay, so let's now, first of all, start with the properties. And meanwhile, sorry, let me just set up something very quickly, which I forgot. I'll just make a copy of the graph, and then we'll talk about some property of that first search. Okay. Let's say we use some example graph over here. And this graph here, notice that this is a single graph. However, you can see that this is the maximum subgraph that's connected. Remember how we call that? Connected components, right? You definitely got to review all the concept for graph, okay? So this is one connected components. This is just another connected components, right? And also, you can notice that in assignment number 1, I also make some explicit assumption. We're assuming that whatever graph you're given to do the breadth first search, there's only one connected component. That means the whole graph is connected. Otherwise, we'll see if your graph is not exactly connected, meaning that you got at least one or more than one connected components, you may have to do depth first search or breadth first search iteratively. You may have to. Okay, let me just write this down. Right, this is kind of the property insight that we can discuss. So first of all, you can see this particular graph is not connected. Number one, this graph is not connected. So that means we got more than one connected components. And if we got more than one connected component, that means we will need multiple passes of traversal. And of course, the traversal we are talking about over here could be DFS or could be BFS. BFS. What does that mean? That means, let's say this. If I say I start my traversal from this particular vertex and do the depth first search, it will reach out as far as it can, and then finally we're going to get this particular connected components. So far, after the first depth first search, we have only covered entirely this particular subgraph. But we haven't really traversed every node in the graph just yet, because the very definition for a graph traversal is to traverse every node and every edge. All right? So think about, in this case, this part over here, this is a subgraph. Subgraph traversed by the first depth first search. Okay, the first depth first search can just traverse only that subgraph. And so somehow your method, your implementation should really say, okay, after I have done this particular one, I gotta make sure every node has been marked as unvisited. Apparently, there's at least one that's not visited, right? So what I should do is, I should really choose an arbitrary node in the remaining vertices that's unvisited and start another depth first search. I gotta keep doing this iteratively until all the vertices are visited. That's kind of the idea, okay? You will see that as one of the question or properties. So what we need to do is, there's another one. Okay, you can think about, let me use a different one. So this is the subgraph over here, another connected components. So this is the connected component traversed by the second depth first search. Okay, so we need two depth first searches to really complete the traversal of the entire graph, because itself is not connected. Right? That's a very important property for depth first search. So a single depth first search, if a single depth first search cannot really traverse all the vertices, that means your graph is not connected. Okay, it's a property. Okay, okay, let's go over some more property here. The most basic one. The running time for the depth first search, of course, it really depends on the implementation strategy we are talking about, especially how you count, how you calculate the incident edges. That's really the most important factor. But let's just say in general, what's going to be the running time? Okay, just the way we kind of perform the depth first search visually, we say that it's going to be big O of n plus n. Just think about we're going to visit every edge and every vertex for at least once. Okay, so here we're just assuming that whenever you're getting some vertex, you can compute its incident edges right away very efficiently. Okay, that's just the assumption. Okay, so let's say runtime. Runtime of depth first search. So it's going to be big O of n plus n. So the m here is the number of vertices. Okay, let me just make sure I'm right. Yep. And then the n here is the number of edges, right? You're just going to visit every node exactly once, and also you're going to mark every edge for exactly once. You don't really repeat the process. So it's going to be exactly n plus n. So there's no polynomial, just in some ways, I think a linear. Okay, but there's a big assumption here, which we'll discuss a little bit more once we talk about another strategy of implementation later. So there is an assumption. Getting a vertex incident edges is big O of 1. Okay, this is a very important assumption. Okay, and in the case of the edge list, it's not big O of 1, I can tell you. So it's not the most efficient way to implement a graph. That doesn't really mean depth first search is not efficient. It just means it's not the most important way, the most efficient way to represent graph. I'll write it down. Okay. So this one here is not the case. To really see why, I can maybe give you some highlights, some hints, maybe on Friday. Okay, not the case for edge list strategy. All right. All right, so that's the first property. Let's see the second one. Okay, you start from somewhere, and then, so this is important, if the number of visited nodes is exactly equal to the number of vertices in the graph, that means the graph is connected. Right? So, for example, hypothetically, let's say for this example graph over here, let's say if I added one more edge to it, hypothetically, let's say between C and F. So that means when I first started with the depth first search, starting with vertex A, I would have also covered this connected component as well as the same components. So that means a single depth first search should be enough. So to really see whether or not your graph is connected, just do a depth first search and try to see if the number of vertices you can end up visiting will be just the same as the total number of vertices. Okay, and the second one, well, it's pretty much relevant. Let's say I got 10 vertices in the graph. After the very first depth first search, I can only visit 8. I got 2 not kind of reachable. So that means I got at least 2 connected components. At least 2, or more than 1. Right? That's pretty much what I just visualized, right? So these 2 are very, very important. Okay. And back edge. Let's revisit what back edge really is. Let's say, for example, I start with A, and then go to B, go to D, right? I try to extend as far as possible. And over here for C here, I got to go, let's say, alphabetical order. When I go back right here, I would have gone back to something I already visited. So this way here forms a cycle, right? So as soon as I have a back edge, that means I have a cycle. Question?
This was more just staring at the graph for a while. The second depth first search we did, what's, like, it doesn't seem to be going, like, shouldn't it go F25?
Ah, okay, good. Notice that? We start with here. Oh, did you actually start? Okay, for the second one, okay, that's important, okay. Did you actually calculate in your mind starting from here or starting from here? Yeah, that's okay. Yeah, that's important. So guys, another hint for you, right? In the actual test, whenever you're doing that first search, one thing is you gotta remember the order of visiting the incident edges. That's something we said. Could be alphabetical or maybe with some exceptions. But number two, you want to know where we start. In this case, I say I start with A right here, but here I say I start with J. Okay. Now, Josh, if you compute it, it's going to be right. Okay. Good question. Okay, so I'll make it explicit. Start vertex of the DFS, and this one here as well will be the start vertex of DFS. Okay, can be arbitrary, really. So implementation-wise, which vertex you really start with doesn't really matter, as long as you can start with something that's valid. That'll be okay. Just visually, it's very easy to see, you know. Yeah. All right, next one. Okay, so if there are no back edges, that means there's no cycle, and the graph is acyclic, right? So just make sure you also understand the English word, right? When you say cyclic versus acyclic, so they mean the opposite meaning. Just be careful as well. Okay. Okay, so for that first search, starting with an arbitrary vertex U, okay, undirected graph. Okay, so the traversal. Okay, let's look at this one carefully. Let's say this. When I actually start with A, I'll write it down as well. When I start with A, what the depth first search can guarantee is not to be able to visit all the nodes in the graph because the graph may not be connected. What it can guarantee is whatever connected component that A belongs to, the depth first search start with that can cover all the vertices in that particular connected components. Okay, I'll write it down. A depth first search starting at vertex A is guaranteed to visit all vertices in the connected components that A belongs to. Okay, this is also said in the slides. I just try to phrase it slightly differently. Okay. No guarantee about visiting everything in the graph, but at least for that particular connected component, right? Of course, if when the graph is connected, there's only a single connected components, right? All right, and then the next one. All right, this one here, discovery edges form a spanning tree. Okay, there's another term I can also mention to you right away, okay? But I believe it's said somewhere, okay? When we talk about graph traversal, let's assume the input graph is simply connected. So only a single traversal will be enough. Let's assume. Let's say we assume the graph G is connected. Okay. Okay, let's talk about some terminology here. So if you try to do a depth first search, a depth first search versus a breadth first search, which I will introduce in the second half, gives a spanning tree of G. And this one here also gives a spanning tree. They share the same property. However, there's some little different term I can mention right away too. Okay, so sometimes this particular spanning tree, as a result from the depth first search, they said DFS tree, which makes sense. And similarly, this one here would be called BFS tree. There's another term for that. Also, it's called level tree. Level in the sense that back in 2101, if you remember, we kind of divide the different nodes in the tree in different levels. Level 0 would be the root, and then level 1, level 2, level 3. That's something we'll see. So the way breadth first search is going to work is really go by level from the starting vertex. Okay? So let me just draw something here right away just to visualize quickly. If you remember back in 2101, so we say that the root is level 0. And then the nodes here will be level 1, and etc. Level 1, level 2, level 3, etc. Okay, terminology. All right, next one. And then if a graph is not connected, in that way, you might need multiple runs for DFS. So you can imagine that your assignment number 1 would have been slightly more difficult if I didn't make that assumption to say your graph as an input is connected. Because in that way, you will just have to somehow wrap around your depth first search within some while loop to say, while I have not visited all the nodes, I got to keep doing depth first search. Okay, I'll write it down too. That's also something for your information. We wouldn't let you do it, but at least you should know. If I do ask you to do it, how would you do it, right? Okay, let's put it here. Okay. So let's say if input graph is not assumed to be connected. Basically, we might need a while loop, something like this. Okay, and then we got to keep doing depth first search. Okay, on some unvisited vertex. And then here we're going to say if the number of visited nodes so far is exactly equal to the number of vertices in the graph. In that case, let's say we have a Boolean variable. Done should be true. Okay, something like that. And you can imagine that we declare that Boolean variable right before the while loop. So Boolean, and then we can say done, initially just false. And then we can simply put condition here, while not done. Of course, if you want, you can also use like a continue, break, return, etc. But it's not very good coding style. But I just want to show you logically, you want to think about, you want to do as many depth first search as necessary as long as you haven't really visited all the nodes in the graph. So you might need multiple depth first search, depending on how many connected components you have. So over here, it is so important to know how many iterations do we have? Right here. How many iterations should we have? Depending on what? The number of connected components, right? That's exactly what we just have been discussing so far, right? Okay. Okay. The number of iterations, the number of connected components. Okay. Conceptually. Of course, it should be some easy extension you can do to assignment number 1, but I just didn't have it. Okay. Okay. Okay, so that's about the properties. Let's now go over some questions about depth first search very quickly. Okay, just answer them. Okay, let's now go right here. So I'll let you guys try. So here we can keep it a little bit informal. Okay, let's say you're given, so these are all the graph applications or questions. We want to ask some question about the input graph. So we all these questions here, you can simply do some depth first search. And somehow by adapting your depth first search a little bit, you will be able to find the answer to each of the questions. Okay? Let's say for the first one, if I want to know, let's say I got a graph. Let's say just I got A here, also I got A here, and also E here, for example. I want to find a path between A and E. Versus if I want to find a path between A and also I. How can the DFS traversal help me? Of course, this will take some imagination, right? So at this level here, you want to think about, you're basically running a depth first search, pretty much like how you would do it in assignment number 1. But how can you somehow adapt the depth first search in a way that you just going to want to compute U and V? There's a path. If there's no path, you can return null. Go ahead, please.
You do a depth first search where U is, and if we can find V, then there's a path. If we can't find V, there is no path.
Yeah, that's pretty much correct. Yeah, pretty much right. Okay, let me make it a little bit more precise. Okay, so let's say this. You can choose either the star vertex of the depth first search to be either U or V. Let's say I choose U. Okay, so basically you can say number 1, start a depth first search from U. You can start from V as well. Since we actually want a path, you might need maybe an array list to keep accumulating the nodes you're visiting. Okay. Maintain a list to store the visited vertices. Okay, for example, so here, let's say you might actually get, let me say I want to get A here, and let's just for A and C. So A here, and then I go to visit B. So far the array list should really store A and B. As soon as I go to C, I put C here. So that's the list I have accumulated so far. As soon as I see that the node I'm visiting is the other one, I know that there's a path. So the array list so far should be the path I want to return. All right. And then number 3, if V is visited, and then you can return the list so far. As soon as you encounter that node, you know that it's reachable from the start vertex U. All right, so we okay with this? Question?
But I think we already keep a stack, like when we run the DFS, I thought we do like a stack where we...
Oh, you said separate. So you definitely need a stack to actually keep track about how you can visit different nodes in the order. But this list over here is something extra because we want to eventually return a path. If the path does exist, you want to return that particular list. It's not a stack. It's something separate.
Yeah, but can we just like run a DFS and then like once we see like, oh, we reached E, and just like stop the DFS and like show whatever is in the stack? Because like doesn't it show the path already? Or?
It might be, but I think this is one way. I want to keep just separate. One is about the stack, it's just about execution order. The other one is just about the path. If you can give it a try, if that one works, it works. Good. Good. Okay, this is one. And the second question here is pretty much the same. Is V reachable from U reachable from V? Right? That one there, similar. Do a depth first search as soon as you reach the node you're looking for, the other one, and then return true. Similar. Okay, so this one is similar to the previous question. calculating path. Similar. Oh, actually, for this one here, I forgot one important case. Because the two vertices you pass, for example, between A and I, there is no path between A and I. In that way, we should return null or empty list as the result, right? So basically, you want to make sure if you're able to go with the depth first search without ever having to return the path, that means the path doesn't exist. Okay, so let me just put number 4 here. If V is never encountered, then the path does not exist. Okay, you got to cover 2 cases. Either it exists or it does not exist. All right, how about this one here? I want to find out all the connected components of G. You can think about each connected component is really the result of a single depth first search, in which case we have mark, the discovery edges, and also back edges. So now what if I want to find out all the connected components in a single graph? What should I do? Before you try out the answer, okay, I'll just try to help you think, right? So this one here, what you should really, one thing we know. Okay, I'll put a star here. A single depth first search can return a single connected components. However, that particular connected components may not cover all the vertices if your graph is itself not connected, right? So now the question is, how do we find out all the connected components? Go ahead.
I would just keep doing a depth first search on nodes that aren't already.
So it's pretty much what we sketched. Oh, sorry. Right here. It's basically what we have to do. We got to keep doing the depth first search, keep marking the vertices and edges until we are done. And you got to keep counting about, so after each depth first search is done, you want to somehow increment some counter for how many connected components you have found so far. Yeah.
For the part 2 again, I still have a question about how.
Okay, sure. This one here?
Yeah, why does the path go from F to H? Wouldn't it go J, F, G, I, H, and do like that?
You mean from F to H? Okay, so if you want to find out a path from F to H, right? So in this case, of course, what you will start the depth first search either from F or you start from H.
I'm saying, like, you started it from J. I'm saying, why, like, because wouldn't you go J and then F, and then we would fully go down this discovery?
So it's a different one, right? So here I'm just trying to say, okay, so this just an example to show to you how depth first search can really visit it and also mark the edges and vertices. However, for this kind of specific question, if you want to find out, let's say a path between 2 specific vertices, the most efficient way for you to do it is to really to start with 1. To take one vertex as a starting point for the depth first search.
I was saying, ignoring that. I'm like the depth first search that you have in the example. Like I'm confused as to how that happened. I thought it would be.
No, it's different. So, so here, the reason I just put A here and J here just show to you the star vertices can be arbitrary, right? So here, because the graph is not connected, so if you start with the vertex A, the depth first search will only cover this particular connected components. And starting from J will only cover this connected components. But if you want to do, let's say, a graph, like a path between U and V, you're going to start with U.
My question was, like, for the, like, you're saying that basically for this we have to do 2 depth first searches, and you show an example where we go from J.
Yes.
I'm confused as to how that one worked, because in my head, we go from, like, if you look at the graph, we go from
Let me take a look. You're just wondering about the marking, right, of the edges.
Yes.
Okay, let me take a look. So this one here, F to G, and then G over here, you go to I.
And then H is still undiscovered. So we would keep going. No?
Could be. Sure. Let me double check on this. And I may have to update that. I was doing that maybe too shortly. So double check. Okay. Okay, that'd be right. Okay, let me definitely double check. But the point here is you might start with the different vertices, but just about the actual marking. Yeah, I know exactly what you mean. But if this is wrong, I will definitely gotta fix it. Okay, let me fix. Okay, let me double check and fix. Okay, good. All right. Okay, let's go over the remaining three, and we'll take a break. Okay, a little bit later break than usual. All right. So if you want to find out spanning tree. Okay, if you want to find a spanning tree of the connected components, let's say here, for this particular subgraph itself is connected. So if I start with A, so the depth first search is going to give me the spanning tree. So this one will be 1, 2, 3, 4, 4 edges, exactly equal to 1, 2, 3, 4, 5 minus 1. That's one of the properties. All right, and of course, this one here may not be correct, so I will forget about this example just for now. Okay, I'll fix that, maybe. All right. So just remember this one here, the number of discovery edges would be equal to the number of edges. So since we assume that G is connected, in G minus 1. Okay, that's a property. Okay, exactly that minus 1. All right. Is a graph connected? Well, similar, right? You just want to know whether you want to go for another iteration. After depth first search, check to see if you have visited all the nodes. Okay. So this one, simply check to see the number of visited nodes. Is it exactly equal to V? It's a question. If yes, it is connected. If no, it is not connected. Okay, so a cycle is basically just try to see the path for you to really find a back edge. Okay, so let's say this. I start from this, A to B, B to C, and then whenever, so now I'm here C, and when I go from C to A, so this is a cycle I can return. It's more like returning a path. Okay, so this one here is really about return the path that leads to a back edge. Okay. Here's the one thing. Okay, so here we're just discussing idea. Hopefully that kind of makes sense conceptually. But what you really want to practice is to maybe take either your solution for your depth first search, or maybe the solution I'm going to release maybe after the submission deadline for assignment number 1. Look at that Java code and think about for each one of them, how can you extend that Java code to implement? Okay, each one of them should really only involve several lines of changes, shouldn't involve too many. So you really want to have the basis for some depth first search implementation and see how you can answer all these questions in graph by extending the depth first search. Okay, that's something you also want to look into. Okay. All right, any questions? Good. Okay, a little bit later break. Sorry about that. Okay, let's now take a short break, and we take attendance as well. All right. So let's now start from slide number 41. Okay. And this is going to be about breadth first search. I think there are several parts about breadth first search. I don't think we can cover every one of them today. I think I might just want to do some very brief introduction talking about the different edges and vertices you can mark. Very similar to the depth first search. You're just going to learn about something called cross edge. And then we do one example just to show to you. And also the data structure you have to use to really keep track about the traversal order. That's also important. Rather than using a stack, you're going to use something else. Okay, very symmetric. Okay, let's see. Okay, breadth search. Okay, BFS as opposed to DFS. Okay, you're still going to start with some arbitrary vertex, and a similar decision you have to make. Given a particular vertex, you have to decide in what order should I really visit its neighbors, like adjacent vertices. You may want to follow alphabetic order or certain order that will be specified to you, right? Just watch out for the order. That's also very important. Okay, let's now go over the principle, okay, and then we'll do some example as well. So just before that, let's talk about how you can mark the edges and vertices. So before the breadth search will start, very similar to depth search, all the vertices are simply unvisited. Okay, I'm just going to use, let's say, red, unvisited. Okay, unvisited, so that means all the nodes A, B, C, D, E, and F. Every one of them is simply unvisited. And also all the nodes, sorry, all the edges are unvisited. Okay? Sorry, unexplored, unmarked. So think about all the edges, we simply have no mark. Okay? Nothing. Okay? That's even before any traversal is done. That's the same as a depth search. Okay? So we got two edges over here. So one is called discovery edge. That one there has the same meaning as the discovery edge in the depth search. So for example, let's say we have already visited A right here. Okay? The way we are actually going to visit the nodes, you're not actually going to try to go for A, B, and then B, E, and then E, C, etc. You don't really go that way. Instead, you're going to say, I want to somehow visit all the adjacent vertices of A first, like a level, before I go to the next level. That's how the breadth search is going to go intuitively. But we're going to see exactly how to do this systematically. So the way it's going to work, at least to mark the discovery edges. So I'm going to go to, first of all, I go to some unvisited nodes, B here, C here, and D here, in this particular order. So after I've done that, I'm going to, all the nodes are visited. That's how I mark the discovery edges. So the fundamental difference is, when you do depth search, you want to go AB, BE, and EC, for example. You want to go as far as possible. However, in the case of the breadth search, you want to go as wide or as broad as possible. Basically, all the adjacent vertices. And then you can use a different data structure to keep track of that. We'll talk about it. Okay? That's about discovery edge. Okay? And then let's say this. Let's say we are now, let's say A has been visited, B, C, and D. And also we got discovery edges just from before. And now, when we, let's say, visit the B here, let's say when we visit B, so now we actually have a chance to go to C alphabetically, right? So this, in some ways, looks a little bit like a back edge in the case of depth search, because we are going to some node that has been visited already. Okay, but this is something called something different. So this one here is actually going to go there. Okay, okay. This one I'm going to write it down. Okay, this is something called cross edge. And cross edge means, okay, so from B to C, right here. So this is called a cross edge, connecting nodes at the same level. So you can think about all these right here, B, C, and D. All these are the nodes at level 1. That means they are one edge apart from A. Because you can see from A to B, it takes exactly one edge. From A to C, it takes one edge. A to D takes one edge. So they are at the same level. Okay? like how far it is from the starting edge, starting vertex. Okay, so these are the three, so these are the two edges we gotta watch out for, discovery and also cross edge. And let's do one complete example just to see, okay? Okay, just about the edges, we're gonna mark exactly that. And let's now talk about this example. Let's say we're given this particular graph, which happens to be a tree, okay? And we want to see how exactly this one can work, first of all, okay? Let me just go over the steps very quickly. We're still gonna start with some, excuse me, we're still gonna start with some vertex V, arbitrary. Let's say we start with A, okay? So the starting point will be A. Let's say we start from there. And then we're going to visit every vertex adjacent to V. For example, for A here, adjacent vertices will be B, C, and D, and etc. And for B here, it's going to be E and F. And for E here, it's going to be G and H, etc. Okay? We're going to do in that particular order. And we want to stay as close as possible, rather than as far as possible. For example, when we already have visited A to B, we don't really try to go to E until we have already visited the entire level right here. That's what I really meant, but as close as possible. Okay, that's something we'll see. And no backtracking. We don't need to. There's no backtracking is a very special phenomenon just for depth first search, not for breadth first search. All right. Let's now just do example here. Okay. So what data structure are we going to use? A queue. Okay, I'll just tell you the answer directly. It's going to be a first in, first out queue. So in the queue, remember you start with the empty queue. You got in queue and dequeue operations, right? Not double-ended queue, just in queue and dequeue. Okay. So I'm gonna do in this way. Let's say this is my queue. So in the slides, you can see that the graph I got actually present the queue vertically, but you can do it horizontally. It doesn't matter. As long as you follow the order for first in, first out consistently, you should be okay. Okay, let's try this. So we start with, first of all, A. So now we visit A. So A should be put in here. And we know that A has the, so now we're going to visit A right away. So from A here, we are going to dequeue A after we have put in the adjacent vertices for B, C, and D. Okay, so I'll write this first step down directly. So before we dequeue A in queue all A's adjacent vertices. I'm sorry it's a little bit small. I know one of your midterm feedback is about the font being too small. I'm not sure how much I can do, but I'll try. What I can do is I can zoom in for you, just in case you're copying, right? If that's really too small, too messy, always let me know. I can rewrite, okay? All right, so let's see this. What we can do is, let's say A here, we got 3 adjacent vertices. Good luck. Okay, so we're gonna get, basically, we're gonna discover B here, discover C here, and discover D here. Oh, just remember. So the pink one, the red one is gonna be discovery edges. Discovery edges. Okay, we start with, also let's now number the vertices about the order. So we start with A, so A will be the first one. Okay, so we're gonna mark 3 discovery edges, B, C, and D, alphabetic. So we're going to get, basically, B, C, and D. We in-queue the adjacent vertices of A right here. After these 3 are in queue, we dequeue A. right? First in, first out, right? And then after this, okay, let me make another note for you. Think about this part here. So these are the adjacent vertices of A. Okay, A is gone. So now, what will be the front of the queue? B. What should we do with B? So B here, we are actually going to discover adjacent vertices, these two, all right? So we are actually going to do 2 here. So think about, we got 2 here, we got, let me just forget about number. Let's just see how the whole thing is going to work, and then I'll put the numbers later, okay? Just a little bit faster in the interest of time. So here for B, I want to take it out. Before I take it out, I need to put another 2 discovery edges. I got E here, I got F over here, okay? So that means I'm going to put E here and F over here, and get rid of it. So think about the E and F over here are the adjacent vertices of B. Okay? So A and B are gone. So now the front of the queue is C. C, nothing. Right? You can see it has no adjacent vertices. So we can get rid of C. And also for D here, also no adjacent vertices. Get rid of D. So now the front of the queue will be E. And we can identify another 2 discovery edges from E, which will be G and H. G and H. So think about G and H over here. So these are the adjacent vertices of E. So after this, we can get rid of E. Okay? And then the next one will be, we look at F, the front of the queue. You can see F here, nothing. So we can get rid of it. And then we try the next one, G here. No adjacent vertices, get rid of it. And for H here, no adjacent vertices, also get rid of it. So that's really the order in which we put the vertices into the queue. It's just about A, and then B, C, D, and then E, F, and then G, H. You really go level by level. All right? So that's really just the intuition I want to talk about. And the next one will be to really use a queue just to see a little bit more about the execution order, etc. So that's something we can do. Okay. All right, any questions? So here we haven't really seen any example about cross edges because the graph itself has no cycle as an undirected graph. But that's okay, we can do that a little bit later. Okay. Any questions so far? Okay, so I would say for your test 1, you will study until slide number 42. Okay, just a very introduction bit about the breadth first search. Okay, some basic. Of course, for the very detailed tracing, you have to know how to do depth first search. So I will also confirm this in the actual PDF as well. I'll try to release it maybe tomorrow morning, the latest. But I already mentioned about the coverage and format in the beginning of the class. Any questions? Okay, so for Wednesday, please bring your questions, and then we can go over any of the topics that we covered so far in the class. And then we're going to focus more on the lecture slides, iPad notes, or any of the tutorial example, etc. That's what we can do. All right. Thank you so much. That's it for today.